us about ultracold Bose gases in flat boxes.
All right, thanks. So, I guess this works. Hello, everyone. Thanks to the organizers for putting all this together and inviting me. And also special thanks to members of my team who actually did the real work. So as Fred said, I will talk today about a uniform Bose gas produced in an optical box trap. And there's various reasons to do that. So we have already heard from Tillman earlier that you can study quantum gases in various geometries, various trap shapes, and they all have some various advantages and disadvantages. And a simple square well, a simple box trap, is experimentally a latecomer to the scene, but from a theoretical point of view, it's kind of the simplest potential you can think of. And for some studies, at least, that comes in very handy. It's very advantageous. So in our case, we are particularly, for now, interested in studying critical phenomena, so studying systems very close to the transition point between two different phases of matter, where the diverging correlation length prevents you from using local density approximation. Okay? And we're interested in studying these systems both in equilibrium and out of equilibrium. But then there's a number of other topics where having a uniform system, which is sort of translational invariant, is either essential or in some ways beneficial. Okay, so today I'm going to go relatively quickly over how we make and characterize BEC in a box potential in equilibrium. And then for most of the talk, I want to focus just on one recent experiment on the Kibble-Zurek critical dynamics of spontaneous symmetry breaking in a homogeneous system. I'll try to do this justice because I think it's kind of the first major thing done in a box potential that is fundamentally different and just could not be done in an inhomogeneous harmonically trapped gas. Okay, so this is what our box trap looks like here on the left, and this is the absorption image of the gas inside the trap. So it's a dark optical trap. So the red rubidium atoms are sitting in the dark here, and they're surrounded by these green repulsive walls. The trap happens to be cylindrical in current experiments, but it could in principle be some other shape as well. So it's formed by intersecting one tube repulsive beam and these two sheet beams which just act as end caps on this kind of Coke can shape. And the way we make this trap is using a spatial light modulator, and because we have a very clever student doing this, we use just one spatial light modulator, which is programmed in such a way that you can send just a single Gaussian beam onto it, and then the spatial light modulator splits the beam into three and makes one tube and two sheets and sends them in different directions. And then you just need to guide the beams a little bit with mirrors. And actually, we align the trap in the end from a computer rather than with mirrors. And so the basic experimental protocol is quite simple once you have the system. So we have to pre-cool the gas in a harmonic trap, and that's because the box has a fixed finite size. And so you basically cool up to the point where the cloud is of the right size to fit inside the box. And then once you put the atom into this dark trap where they feel no force from the trap itself except at the walls, then there's still one last thing you have to do, which is to cancel gravity. Because if you don't cancel gravity, then the atoms actually live in a linear vertical potential. Okay? So for our purposes, we have to cancel gravity at about 10 to the minus 4 level, which we use, for which we use a magnetic field gradient. And so once you have the cloud in this uniform system, then you can cool it more. And this works very simply. It's exactly the same kind of evaporative cooling that you do in a harmonic trap. You just lower the height of the walls and evaporate the gas in a forced manner. And this is kind of the basic setup for the trap. Now you can change geometries. And the system methods are also compatible with Feshbach resonances or adding optical lattices or doing this with fermions or what have you. So the first thing you see as you try to make a BEC in a box trap is that unlike any experiments we have seen before with harmonic traps, but actually exactly like we've been taught in school when we were undergrads, in this case, condensation occurs only in momentum space and not in real space. So if you look at the gas in situ, as you cool it and even cross the sea, basically nothing happens, or at least nothing good happens. All you see is that you're losing atoms, but and the density is dropping, but you don't see the effect of cooling directly. However, if you look in the momentum space, in the time of flight, then you see that the signature of condensation is qualitatively quite similar to the harmonic trap case. So you see it's subpointed by modal momentum distribution. And for this demonstration, we picked an elongated trap so that you can also see the inversion of the aspect ratio of the cloud. Okay, so that's very qualitative. More quantitative, to see that you have condensation in a uniform system and not a harmonic one or something else. You measure the critical point. So basically, you measure how the critical atom number scales with temperature. And again, as you know, we were all taught long ago in school, in this case, NC scales as t to the 3/2, as opposed to the t cubed that we have more recently gotten used to in harmonic traps. And so from these thermodynamic measurements and some others that I'm not showing you, we can also assess exactly how good, how perfect is our box trap. And it turns out it's quite good. So some leading order correction that we see to the perfectly flat bottom, to the perfect square well, is at the level of r to the 15 or r to the 20 leading term correction. So for all practical purposes, it's basically a perfect box. Then the next thing we have done is we also looked at the properties of the BEC itself at very low temperature. So where we have basically a quasi-pure BEC, and we did this mostly using a standard two-photon Bragg spectroscopy, as was first applied to ultracold atoms by Bill and Wolfgang about 15 years ago. I'm not going to spend much time on this. I mean, the short message is that basically it all makes sense. So we have looked at the momentum distribution of the condensed atoms, and the spread of the momenta is basically given by the Hadzibabic limit, and we changed the box size, the spread of the momentum changes accordingly. We have looked at the interaction energy by looking at the shift of the Bragg spectrum, and that satisfies, agrees with the simple mean field theory. And we have also studied the time of flight expansion of the BEC from the box trap. Here you see that when you release a BEC from a box trap, it develops this kind of diamond shape. And again, that is understandable with the mean field theory, just with the Gross-Pitevsky equation. There's no analytical solution, so we have to do numerics, but then it all fits. Okay, so that's my run-through. The things that we knew in advance. In fact, we knew them even before all the experiments of harmonically trapped gases. It's just now we're seeing them for the first time experimentally. But now I want to switch to the main topic of this talk, which is the dynamics of spontaneous symmetry breaking in a homogeneous system. In our case, the Bose gas, but most of this is much more general. And so it's a broader actually topic than just Kibble-Jurek theory. But most commonly, we think about this in the language of Kibble-Jurek model. So the basic idea of the Kibble-Jurek theory is that whenever you cross a continuous phase transition at a finite rate in a homogeneous system, you end up with these domains, independent domains of the system, within the system, which display somehow a different choice of the symmetry breaking order parameter. Okay? And in our case, this is a different phase of the BEC. But in a different case, it can be the direction in which the magnetization points, or it can be the large-scale structures that we have in the universe, which have more or less matter or antimatter and things like that. In fact, historically, the whole theory was introduced for the first time in order to explain the large scales in the universe. Okay? And the faster you go through the transition, the smaller these domains are going to be. Now, more theoretically, slightly more theoretically for now, what is behind this picture is that in order to develop, say, a BEC with a uniform phase, the correlation length in the system has to diverge above TC, okay? So in the critical region, the whole system starts kind of fluctuating in unison. This is what we often know as critical opalescence, okay? And then if the whole system is fluctuating in unison, then when you hit TC, the whole system can jointly choose a particular phase or a particular direction of magnetization or what have you, okay? However, for the correlation length to diverge, it also takes a diverging time. This is commonly known as critical slowing down, okay? And so if you're going through the transition at some finite rate, at some point the system can no longer follow adiabatically. The correlation length has no time to span the whole system before you run through TC, and so you end up with these domains which do not have time to communicate with each other and coordinate the choice of the phase of the BEC or whatever the other parameter is. So qualitatively, that's the basic idea. Now quantitatively, this Kibble-Jurek theory also makes some strong prediction about some universal scaling laws for this domain size as a function of quench rate. That's the real content of the theory. Otherwise, qualitatively, the idea is older and broader than the Kibble-Jurek theory. Okay, So I'll show you just a little bit of maths, at least to introduce the language I'm going to need that I'm going to refer to later in the talk. So we can define the distance from the critical point in a dimensionless fashion. This is this epsilon here, t minus tc, just scaled to tc, okay? And then in equilibrium, again, this is more general than Kibble-Jurek, the correlation length, the divergence of the correlation length is controlled by this critical exponent nu, okay, which is a characteristic of a particular universality class, which in our case is the 3D XY model. And then the diverging relaxation time is linked to psi via another critical exponent z, which is called the dynamical critical exponent, okay? So this is all pre-KZ, and then where the Kibble-Jurek theory comes in, unfortunately you cannot see well on this slide. Can anyone in the back see that the central part is gray? No? Okay, fine. Okay, where the Kibble-Jurek hypothesis comes in is that this is a very complicated problem, so they introduce some intuitive simplifying assumptions. And what they say, this so-called adiabatic impulse adiabatic approximation, is that when you're away from the critical point, the system follows adiabatically as you tune the temperature, and then that will also be true on the other side over here. But inside the critical region where you cannot follow adiabatically, they say the correlation lengths are basically frozen, okay? And the point where it freezes, it's, again, intuitively very simple. It's like as you move along this line, as you're cooling the system, they say at the point where your relaxation time is equal to the time you have left until you're going to hit Tc, that's where the correlation length freezes. There's no chance to follow adiabatically anymore, okay? And so with these, I'm not doing it here, but it's really just a few lines if you try at home. With these few equations and a few lines of algebra, you get this universal prediction of the Kibble-Jurek scaling law, which tells you that the domain size scales with the sum power of the quench time, and this power is just a function of nu and z, okay? So it's different for a different universality class, but for all systems in the same universality class, it's supposed to be the same. Okay, so qualitatively, this kind of physics has been seen all over the place. For more than 20 years, it has been seen in all kinds of systems, from liquid crystals, superfluid helium, trapped ions. I don't have pictures also, but also here, but also superconducting systems, array of Josephson junctions, and then more recently with ions and atoms. And at least qualitatively, all these experiments show the same ideas. However, for one reason or another, a direct quantitative comparison with the theory has remained elusive to this date. In some cases, the problem is the system is not homogeneous, so that messes things up. In some cases, there's doubts about the nature of the transition that's actually being crossed and so forth. So there's many experimental issues. But also on the theoretical side, it's still a matter of some debate exactly how valid and how accurate is this freeze-out hypothesis which allows us to derive the universal scaling laws. So let's see what we can do with cold atoms in a box. So before I get into anything serious, just very qualitatively, this is what you see if you cool the system at different rates, and then just look in time of flight at what the BC looks like. So here, if you go very slow, I'll get into numbers later. If you go very slow, then you make a nice BC with a uniform phase across the system, and in time of flight, this develops this characteristic diamond shape. And then if you, on the other hand, if you go to the same temperature, same atom number, but just not quite as slow, then you end up with phasing homogeneities inside the trap, and when you do the time of flight, that turns into density inhomogeneities, okay? This has been seen before in other things like elongated and 1D systems, for example, of cold atoms, how phasing homogeneities turn into density inhomogeneities, okay? But we're not going to use this for anything very quantitative. This is just sort of to give you an idea. To get quantitative, what we do is we pretty directly measure the first order 2-point correlation functions, G1, which is the measure of coherence in the system, okay? And there's two ways to do that. There's a way we pursued for a while, which is basically to measure the momentum distribution using Bragg spectroscopy as before, and then you can obtain G1 by a Fourier transform of the momentum distribution, okay? And then there's a better way, which I quite accidentally learned from Bill about 4 or 5 months ago when I was visiting here, because they invented it about 15 years ago and applied it to a harmonically trapped gas, which is to do a sort of Ramsey version of the Bragg spectroscopy. So instead of doing one long pulse, you do two separated short Bragg pulses, and that actually allows you to do a measurement directly in real space rather than in momentum space, okay? This is too quick and obscure. I'll try to do it a little bit more justice, but still try to do it in a single slide. So a two-photon Bragg transition basically couples a stationary state and the moving state with the speed v recoil. Okay? And so what we do is we start with some BEC, okay, which might have some domains. It might have non-uniform phase. And then with the first Bragg pulse, you make a small copy of this cloud, which is moving away with recoil velocity. Okay? And then sometime later, these two copies are displaced, but they're still overlapping in one region. Okay? And so what you have in this overlapping region is that on top of each other, you have moving atoms, which actually originated at the bottom, and the stationary atoms, which are always there. Okay? So these two classes of atoms, depending on your domain structure, may not have the same initial phase. Okay? And so with the second Bragg pulse, you basically interfere these atoms which originate from different parts of the cloud, and the final density of the recoiling atom in this overlapping region depends on what were the initial phases between these different domains. Okay? I hope that conveys some vague idea of what we're doing. And then, in principle, you could even look at these domains, but they're very, very small. It's certainly below our imaging resolution. But you don't need to do that. You can just wait for these guys to separate and then count how many atoms have recoiled after the second pulse. And then, again, with a few lines of algebra, you can show that this diffracted fraction is very simply related to the G1 as usually defined in condensed matter. There's some trivial constants involved, and then G1 is multiplied by this triangular function 1 minus x over L, which is basically just the measure of this overlap because interference happens only in the overlap region. So to see that this works, we first applied this to an equilibrium BEC, and in this case, the simplest case of a pure BEC, so it's 100% condensed fraction. We cooled slowly, we cooled carefully, and we eliminated all the thermals. And so in this case, you expect the G1, as you know it, to be simply 1. It's 100% condensed fraction. So the thing we actually measure is multiplied by 1 minus x over L. You should see just this triangular function. Indeed, that's what we see. We start at 1, just go to 0 at the edge of the system. Now, for understanding of what is coming up in a minute, it's also instructive to look at an equilibrium gas, but not very cold. Okay? So here we are just at 0.7 Tc. So there's a significant thermal fraction, and that's what we see in the initial fast decay of G1. But the nice thing is you see is that even though the condensed fraction is not so high, the coherence still spans the whole system. Okay? This is one of the differences between a harmonic trap and a box. Right? In a box, it doesn't matter how many atoms are in the BEC. The BEC is always the same size. So basically, the slope of this light blue line is the condensed fraction. And so with these two equilibrium measurements as a backdrop, you can quickly see that if you do a quench experiment, you get a G1 which has absolutely no consistent equilibrium interpretation. Okay? So here in red, what we have is something that is very cold. T over Tc is less than 0.2. Phase space density is more than 30. Okay? And yet the coherence extends only over a small fraction of the system. Okay? And how far it goes depends on how quickly you quench. Now, of course, you could be a devil's advocate and say, like, well, wait, maybe this is just somehow thermal. Maybe this is just lambda correlations, right? But if that is lambda, then you get something completely ridiculous. Then you get the temperature has to be 200 picokelvin. The phase space density is 1,000. So there's just no way to make it consistent within equilibrium picture. And first, we experimentally found that this quenched G1s are treated quite nicely with a simple exponential, which gives us a simple, robust way to extract the coherence length. But then later on, we also did some simulations which confirmed that this exponential form is right, and that this L is basically 2 digits equal to the average domain size D. I'll still keep calling it L just because we're doing experiments, but it is the same thing as D. Okay, so what do we expect? Let me remind you of the math a little bit. I have already shown you this power law scaling with a universal exponent, but I didn't tell you what exponent we're looking for. So for our universality class, the mean field predicts that nu is 1/2 and z is 2, which means b is 1/4. And the dynamical critical theory, which goes back to Bert Halpering and Pierre Hohenberg and people in the 60s, predicts that nu is 2/3 and z is 3/2, and so b is 1/3. So these two numbers are not very different from each other. That's not so good for experimentalists. But certainly they're very, very different from the kind of number that you would get if you do a sort of modified Kibble-Jurek theory for a harmonic trap. Okay, but there's a bigger problem. You stare at these equations as an experimentalist for a while, trying to figure out your parameters that you want to explore, and you realize this doesn't even make sense. Because it cannot be at least the whole story. Because if I look at the typical numbers here, this tells me that it's going to take me an hour to make a pure BEC. And that's not true. We have made it before in like 5 seconds or 10 seconds. Right? And then you realize it's not you. Sorry, it's not them, it is you, right? That doesn't understand everything yet. You start thinking about the conditions under which the KZ theory is actually supposed to be applicable, and as you will see over the next few slides, it all kind of falls together in the end. And actually, in the end, we understood and experimentally demonstrated more about the theory than we set out to do in the first place. So to do this, I'm going to have to show you two different quench protocols, but let's start with the simple one. So the simple quench protocol is the first thing you would think of. Let's just cool at different rates, okay? And we cool at different rates in a sort of self-similar fashion, right? So what we do is we always follow exactly this trajectory. This is data on top of some simple polynomial fit. We always follow exactly this trajectory. We always start with the same atom number at 2.3 Tc. We always go to very low temperature. We always cross the critical temperature about 3/4 of the way and so forth. And the only thing we do is we rescale the total time, okay? So this quench time is then the parameter that should enter the Kibble-Zurich scaling law. And we always do the measurement at the end because you don't want the trivial thermal excitations to confuse your G1 measurement, right? As you have shown you before, the thermals can also affect the decay of G1 at short distances, right? You want just the domain size to affect your G1 measurement, okay? And so what we see is this. It starts off promising, okay? So for fast quenches, we see a very slow growth of L, okay? Which agrees with both mean field and beyond mean field theory, but it's in the ballpark for the Kibble-Zurich scaling law. But then at some point, this scaling breaks down and L starts growing faster. It starts approaching the system size. And this line, if you extended it over here, this is the line where we have to go for an hour in order to get the system size. So we knew this was coming experimentally, okay? We knew that it cannot be true forever because we know we can make a BC in less than an hour. The nice thing is that now that we understand everything, it turns out we can also explain this within the Kibble-Zurich theory. In some sense, it's part of the theory, this breakdown of the scaling. So this is the basic idea. If you look at the algebra, you see that this frozen out time, where the system doesn't evolve because of the critical slowing down, scales as the root of the quench time, okay? And so what it means is that when you have a fast quench, then you have this kind of picture, right? This is your total cooling time, and this is the T hat, the freeze out time, okay? And so in this case, you complete your cooling, you measure G1, you do everything before the system had any chance to evolve, okay? Had any chance to unfreeze and coarsen, right? And so in that case, you observe the KZ scaling. But now if you just multiply all your times by a factor of 10, the freeze out time goes up only a factor of 3, okay? And so suddenly you have switched to this kind of situation, where maybe you did not cross the transition adiabatically, but the system gets to unfreeze and coarsen or evolve before you actually do the measurement. And so because it starts healing, you end up seeing L, which is above this line. So that's pleasing that it makes sense, but we still wanted more. So we said, okay, this scaling law has an unknown prefactor. It's certainly not universal, and it's not even known for us. But since we see where we switch from scenario A to scenario B, we can actually fix the prefactor and make predictions that we can test further with a different quench protocol. So this is the second quench protocol. So here shown in orange. So what we do is we follow this highway of the blue quench trajectory, just as before. We cross TC, okay? The domain seems supposedly formed, and then, after we have crossed TC, at some point we introduce this kink and just complete the cooling as fast as possible. You can think of it just as a way of measuring domain size at different points. So we get to measure G1 before the system had a chance to evolve. And when I say as fast as possible, it's still slow enough for collision rate and so forth, so temperature still falls. And so what do we see? Well, there's two scenarios. If the original quench was already fast enough, then this doesn't do anything. Once you have crossed TC and you're still in the frozen regime, you can accelerate all you like. The domain size is already fixed. However, if the original quench was slow enough, the system was going to unfreeze, you see something very nice, which directly supports this Kibble-Zurich freeze-out hypothesis. You see that for quite a while, after you have crossed the critical point, L remains constant, okay? And only then it takes off. And moreover, we can now predict what the freeze-out time is supposed to be, and that's shown here by this black arrow. And it fits quite nicely. And then the last point is like where this frozen value of L follows the KZ scaling. And it does, okay? So this is what I've shown you before. Now you do the second protocol, and as long as you measure anywhere in this plateau, before the system unfreezes, you're going to fall onto the Kibble-Zurich line. For green and purple, it's also true, but it's kind of trivially true. And so now we know how to extend the range. We know how to do measurements over a much bigger range and take more data in order to improve our measurement of the Kibble-Zurich exponent. And so this is the summary, combining the two kinds of protocols. And the final number is B equals 0.34 with an error of 0.04. And let me remind you, the mean field is a quarter, the beyond mean field is a third. So now we have actually enough data to distinguish the mean field in the beyond mean field theory. We can exclude the mean field at about 2 sigma level. And so with everything fitting in, we can now also deduce the critical exponents for the BEC, the interacting BEC phase transition. And what we get is that nu is 0.68, which agrees with numerous measurements in helium, which are more accurate and precise than ours. It also agrees with the measurement that the Tillman managed to squeeze out of the harmonic trap it's a few years ago. So that's all nice, but it's sort of been done before. It's just kind of reassuring that we all agree. But more importantly, we can also now measure the dynamical critical exponent, z equals 1.5, which is again in agreement with 3/2. And this is something which has not been measured before, not just in cold atoms. It has not been measured in helium either. And it's sort of a central piece of the dynamical critical theory, because this z has to be 3/2, for example, in order for the heat capacity not to diverge and things like that. And it has not been confirmed until now. Okay. So with that, I would like to conclude. So to summarize, combining knowledge from 2 different kinds of quench protocols, we have managed to directly verify the validity of this freeze-out picture of the adiabatic impulse adiabatic approximation due to critical slowing down near the critical point. And then we can measure the Kibble-Zurich scaling law for a homogeneous system, and we observe the beyond mean field scaling law, which is again the first for any system, not just for cold atoms, right? It's not been done ever before. And then for our universality class, we measure the critical exponent. So this is for any universality class. It's the first time it's done as far as I know. And then for our universality class, we extract the critical exponents, which nu is kind of reassuring. It agrees with what was done before. But the dynamical critical exponent z is sort of the bigger new result. And finally, I would like to point out, you should also see Jean's talk on Thursday, who's going to talk on similar physics and also some beyond mean field physics for a 2D system. And this is just a summary of our early equilibrium work that I ran through at the beginning of the talk. Thank you for your attention.
Thank you for these very exciting new results. I'm sure there are many questions. So, Bill?
So this is really neat stuff.
Thank you.
So as you were talking about it, I was thinking about a question which you then answered. In other words, the question was, well, what about the idea that after you cross the transition and make these boundaries, you know that they're going to heal? Yeah. And so you addressed that. But of course, people have been thinking about this for many, many years. So what I'm wondering is, are the numbers that you get from this experimental way of understanding what this sort of healing time is, does this agree with all the theory that had been done before to get at what happens to a BEC if you do a really sudden quench, and then you know that it's going to take a while. So is that all consistent? And does it make any difference whether you continue to evaporate?
Okay, these are different kinds of questions. So the first thing is, first I want to distinguish 2 times. Okay, one relevant time is how long nothing happens, and the other relevant time is like what is the time scale over which the healing happens after that. Okay, we have addressed only the first one. Okay, so what we see, that's what we see here, right? Right. This freeze out time before the thing starts to evolve, and that agrees reasonably. I mean, we didn't want to presume things, okay, in this scaling, general scaling law that we have there, but it makes sense. There's some numerical prefactor which everyone knows is not known, and now we get like 1.5 or something like that. So that makes sense. Now, what happens afterwards? The coarsening dynamics is another 50 years of discussion, theoretical, and that's for the next experiment. We have taken 1 or 2 curves, but we have nothing conclusive to say, right? And the last thing one hint I can give you, which is related to your story, but does it matter where you evaporate? It actually seems, but I should not be quoted on this. If I give you a budget of, say, 5 seconds, it seems better to go down to lowest temperature in 3 seconds and wait for 2 than to actually go carefully. Okay, and that's maybe some hint about, maybe it's better to have more evolution in the low-level trap. But, we have not tried to go down and then raise the trap again. So, this is very preliminary hint.
Okay.
So there's a question here.
So how do you measure the temperature of a BC in a box potential?
It's a good question. So we do usual time of flight. I mean, you need about 6 months of work to figure out how to fit things properly, because all these polylog functions are now different, and you have to get used to them. But in long enough time of flight, we cancel gravity anyway, so we can do very long time of flight, right? And so you have to do longer time of flight because the energy scales are lower and the initial size is bigger. So it takes quite a while. I mean, it takes a BC more than 15 milliseconds to just get out of the box, to start spreading a little bit. And the thermals in about 100 milliseconds, you can see the tails. Right?
Thank you.
I think Maciek has something Polish to ask.
Here's the next one.
So my question is, it seems like this whole Kibble-Zurich thing is in the thermodynamic limit.
Yep.
And so what do you think the effect is of having a finite number of particles?
Mm-hmm. I don't know. I know where finite number sometimes comes in, and it's okay for us, but it was a problem for many other experiments. So what certainly becomes a problem is that the number of domains is not much larger than 1. Okay, because then this large number statistics don't work. Random walks in phase, with phases don't work, and so forth. Right? And so we, through luck, maybe more than intelligence, have ended up in a situation where all the numbers are reasonable. So we have 100 to 1,000 domains in the system, and we have 100 to 1,000 particles in each domain, right? Very typically, right? So we can sort of call all numbers large, right? But historically, the problem was more that the number of domains is small, and then the scaling laws get modified. And
right, because it seems like the reason you need this whole freeze-out thing in the first place is because there's infinitely far to go, and at some point, no matter how fast or slow you go through the...
Yes, that's right. Okay, so another effect of the finite size, of course, is that for us, there exists a time, even though it's an hour, but there exists a time where you can directly produce a pure BSE, okay? Whereas in thermodynamic theory, it's just not possible, okay? But for us, it's an hour, whereas in a harmonic trap, it's 10 seconds or 5 seconds or something like that. Because in a harmonic trap, you have different scaling. I mean, it's not really the same theory, because the guy in the center always wins and imposes the phase on everyone else. And mathematically, if you try to modify theory, the way that comes out is that this B is bigger than 1. Now, if B is bigger than 1, then you just need 10 collision times and you get a BC, or 100, whatever. But for us, you need 100,000 collision times to directly produce a pure BC.
Thank you.
Okay, last question from Maciej.
I'm curious what Maciej was.
You mentioned that in principle you can include lattice here. Now, harmonic lattice in the case of multi-insulator superfluid transition is maybe considered as a nuisance because, as far as I remember, it smoothes there is no transition, there is crossover. There are these papers from Stuttgart by Alejandro. And on the other hand, the lattice is a blessing because you have the wedding cake.
Yes, I agree.
So what will be happening here?
I don't know. I'm torn about it. But what I would suggest, I don't know what I would suggest. But I expected this kind of question, why did you wait so long for the box? And indeed, for detecting phases, harmonic trap is better because you get automatically wide search over very many mu values and so forth. I don't know. Maybe the best thing would be to actually start with the box, but then put a linear gradient if you want. It's easy to mess things up, and instead of having this wedding cake, have big regimes. And so if you have a little gradient, you will have different commensurate fillings in different places, right? And once you have your signal, you can tune down the gradient if you want to spread a particular filling factor over most of the system or something like that. But I agree, in that case, just perfect box with no additional tool is a little bit of a problem as well, because it's very hard to get the commensurate filling. Right? Yes, but I think with some little, I'm sure it's good to have new knobs. Having some gradient which we tune, I think will give you all the benefits of both worlds.
Okay, so let's close the discussion here, and let's thank Zoran and all the speakers for this wonderful session. We have one announcement from